All right, I'll be talking about recent progress, focusing on theoretical models this morning. So the goal of the theoretical effort is to model excess heat in the Fleischmann-Pons experiment. So lots of experiments have shown an excess heat effect. There's no accepted theoretical explanation within our community or within the mainstream. Our approach is based on phonon exchange. For the excess heat, the thought is to start out with a D2 in either di-deuterium form, sort of something like a molecule, have it make a transition to helium-4, mediated by phonon exchange, transfer the excitation elsewhere, and the elsewhere, in order to make energy conservation work, involves a large number of excited metastable nuclei. Then these metastable nuclei within the model, they down-convert and transfer the energy into the vibrations. There are two features of this. The biggest feature is that any theory that has to do with the Fleischmann-Pons experiment that seeks to address cold fusion has to deal with the absence of energetic nuclear particles. So that's where the down conversion comes in. The second thing is that if it's done the way I'm advocating, then the tunneling factor comes in only once rather than twice. And since the e to the minus g is on the order of 10 to the minus 37th, having it show up only as 10 to the minus 37th and not 10 to the minus 74, well, every 37 orders of magnitude helps. So as a result, with this model, the rates that are estimated from it out of the box, without having to do any heroic screening effects, are on the order of what's observed in experiment. So I have a cartoon that shows how the idea works. I start with D2 excited. Phonon exchange makes it go down to the helium-4 state, but when that happens, then many nuclei, on the order of 100 or more, are promoted. Phonon exchange, for this to work, phonon exchange has to be very fast. Then the excited state metastables then down convert, exchanging phonons, back and forth and back and forth. So in the end, you've turned D2 into helium-4, and the energy has gone into vibrations. And so that's the picture. Where does it happen? Well, I'm of the opinion that bulk palladium deuteride is inert, mostly because the deuterons in octahedral sites are too far apart from one another to do very much. On the other hand, if you have a palladium vacancy, the electron density is lower, and you have octahedral and tetrahedral sites in the vicinity of a vacancy. The vacancy can hold 6 octahedral deuterons and 8 tetrahedral deuterons. So there's 14 sites there. If you get 8 or less, there's places that aren't next to one another. When number 9 goes in, you have an O site and a T site next to one another. I'm not sure that that's close enough to do you any good, but on the other hand, it can isomerize with the di-deuterium state, the molecular state. Let me talk about excitation transfer. So how would we prove this mechanism? The big headache is that if the excess heat works properly in the Fleischmann-Pons experiment, there's no energetic nuclei to come out. So you can't put a detector next to it and see what's going on. This is in contrast to normal incoherent reactions. So if you have an accelerator reaction and one deuteron hits another one, you get a 3+1 final state, and you can use detectors to see what comes out, and the energies and the products, and you can learn everything there is to know about it. That's not true for the Fleischmann-Pons experiment, which is what has made theoretical progress on models and understanding mechanisms so difficult for 3 decades. So From my perspective, we need a new experiment. If it works the way I think, we need to see excitation moving from one nucleus to another nucleus. And from my perspective, as I've suggested, in a normal Fleisch and Pons experiment, you have no way to see that directly. So we need a new experiment where we can look at it and see it directly. So how does excitation transfer work, at least in the way that I'm thinking about? We might have an excited nucleus and a ground state nucleus, which is the identical other than the excitation. And if excitation works, then you go bing, and the excitation gets from one nucleus to the other nucleus. Now, how it does that in detail, in my model, phonon exchange, you get a phonon exchange for this nucleus, you get a phonon exchange for that nucleus. Off-resonant states are involved, and there's a lot of physics to describe this relatively simple process. But this excitation transfer process, according to my models, lies at the heart of excess heat, tritium production, neutron production, low-level nuclear emission, upconversion, many other effects. One effect that this doesn't apply to directly would be Ken Schulter's EVOs. And later, Lutz Jaetner will present a model which I think is very relevant for that, which my models don't deal with. Okay, so nuclear excitation transfer. What would we do for an experiment? We'd like to start with some excited nuclei. We'd like to make sure there's similar nuclei around that are in the ground state. We'd like to add some phonons. As it turns out, you grind through the math. The math suggests that the terahertz phonons are much more effective at making this work than kilohertz or megahertz vibrations. Resonant excitation transfer is the easiest to make work from theory, and easiest in the sense that if you start to make excitation transfer work at all, resonant process would be the first one to kick in and turn on. And in principle, you'd be able to see that excitation transfer happens because you could get a modification of the angular distribution. So if you have no excitation transfer and you have excited nuclei, they'll emit in a dipole pattern, but with random orientation. So your detectors will think that the radiation comes off isotropically. On the other hand, if you have excitation transfer that's resonant, then the excitation is simultaneously as quantum mechanically at a number of different sites. So when the decay happens originating at numerous sites. Now, if there's local order in the lattice, then that can give you an interference effect and send the radiation off at a one direction preferred over a different one. I think we've seen that in some of our experiments. The non-resonant excitation transfer is the next easiest to make happen. And non-resonant means that you exchange one or more phonons in the process. So as a result, after you do your excitation, the coupled nuclear vibrational system is now mixed, such that when you decay, you get a spread associated with that mixing. So you might add some phonons or subtract some phonons from the energy of the nuclear decay. In addition, it means that you lose the phase coherence, because every time you do some steps, you pick up or lose some phonons, so the different channels are no longer in phase, so you lose the angular anisotropy. So for example, we'll be talking some about delocalization, which is non-resonant excitation transfer on the 14.4 keV line. And so far, we don't have evidence for an angular anisotropy on that line. An experiment was done in 2017. In those days, we were trying to make our vibrations with a megahertz transducer. Florian ran the experiment, And it was a failure in the sense that we didn't see a response, a prompt response when we put megahertz vibrations on. On the other hand, it was a success in that the 14.4 keV line showed a transient decay here. So the idea is that the cobalt-57 decays to the excited state at 136 keV. This lives for a little bit less than 10 nanoseconds. 88% of the time it decays to the 14.4. And so the transition we're looking at is this one. It's of nuclear origin. And the way to understand this is that this line here is the 271 half-life, the normal decay. Probably what happened is before the experiment was decaying like this, Florian twisted down some screws, and that made the excitation go up, not over the whole sample, but for part of the sample that could go through some small hole in a coarse mesh. So a cartoon version of it looks like this. We have a steel plate here. We have a residue here where cobalt-57 was evaporated on the steel. The evaporation is non-uniform. So there's more cobalt-57, more iron-57 here, less here. And there was a mesh. It had other holes, but I'm just drawing one of them here for simplicity. So where the bright spot is goes to the detector. Now, if excitation happens and you can transfer from one site to another site, well, the excitation transfer process, at least according to our current interpretation, is pretty democratic. So it's going to keep on transferring from one place to another place, except that if there happens to be more cobalt-57, the sample we had was probably 10 years old or 5 years old or something. So many cobalt-57 decayed already. So it was primarily iron-57 in the residue. So as a result, there's 2% iron-57 in the steel, but we think there was mostly iron-57 in the residue. And so where it was strongest is where the most iron-57 is. So the simplest way to think about it is the rich get richer, which has been known since antiquity. And that's what would give us the more intense signal in the detector. And then after a while, the stress would be released, there'd be fewer phonons, and it would relax back to its normal state, which is what we see. So how to prove that it's excitation transfer? We need an imaging experiment. We'd like to see where the excitation goes, namely, if that picture is correct, then that means that there's places we should be able to see it increase, there's places where we should be able to see it decrease. An attempt to do this was done by Siwan Liu and Florian providing a great deal of experimental support for the experiments. And increases of emission was found at a hot spot, but also a place was found where the emission decreased. And that was very interesting. Now, Florian has a very much stronger version of this, which shows in one experiment the hot part increasing, the cold part, or the part less intense decreasing. And the excitation transfer looks like it moves more than a millimeter. Given that every step is probably 100 angstroms, having it move a millimeter means that it happens a lot, and it happens very fast, which is a good thing because that's what the models need to make excess heat work. Let me talk a little bit about the theory. So the experiments show the effect, and so forth and so forth. What does theory say? And I talked about some preliminary results at ICCF22. So we have a model. We have some vibrations, phonon modes here. We have nuclei with levels, different levels, and we have here a boost correction to the nucleon-nucleon interaction, which provides the coupling. So if we calculate the resonant case for the E1, we get a complicated formula. And for the experiments we're doing, it's a magnetic transition, so it ends up being twice as complicated. And when we look at the answer, we figure out that destructive interference basically makes hardly anything happen at all. At ICCF21, I had some preliminary results suggesting that the destructive interference got to be removed for this. And that's what you get for trying to present a preliminary theory result at a conference. It was incorrect. And when I went back and did it right, I found that the destructive interference was very severe. So how do you get rid of the destructive interference if the experiment's working? That means there has to be a way. Now in 2002, I proposed that a loss mechanism could make it work. So the idea for up conversion or down conversion, you have the excitation transfer and it's off resonant, so you can accumulate phonons or lose phonons depending on whether you're going down or up. And if there's asymmetric loss, it breaks the destructive interference and makes the rates be orders and orders of magnitude greater. So I thought, aha, now we have these experimental results. We're seeing excitation transfer in the lab. We have a theory. Let me add loss and make it work. So if I add loss for the E1 case, I get this expression. And if I plug in numbers, I find out that it's orders of magnitude better than not having loss. But if I try to connect with Florian's experiments, it doesn't work. This was very discouraging and very depressing because I'd been thinking that loss would fix everything. And now that we have some data, and I can compare the model against the data, I find that it comes up short. And that caused many sleepless nights, lots of angst, banging head against the wall. You know the drill. Last fall, there was a brainstorm, and the brainstorm, you call it a brainstorm to make it sound good, but it was really an act of desperation. The act of desperation says, if the energy levels off of resonance shift, that can also break the destructive interference. So, for example, you start here, which would have one excited nucleus, one ground state nucleus, and you'd end up here where they'd switch, but you have to go through intermediate states where they're both excited or they're both de-excited. So the reason there's destructive interference is because this and this are symmetric normally. But if you have energy shifts that are asymmetric, then if they're off-resonant and asymmetric, then this turns into this. And this is now no longer symmetric. Going up and going down is different, which means the contributions can't kill each other off to precision. So this kind of model breaks the destructive interference. If you calculate the E1 case for resonant excitation transfer, you get the off-resonant energy parameters showing up. It destroys the destructive interference. This is really big. The resulting expressions now are big enough that they can match with experiment. And also, because the up conversion, the down conversion is composed of many excitation transfer steps, then this also applies directly to up conversion and down conversion for excess heat production. So this was a really, really interesting idea. Now the only thing that we need to figure out is whether the energy levels actually do shift off of resonance. So the question is, how big are these shifts off of resonance? So I decided to look at the deuteron as being the simplest problem that I could analyze. So I went ahead and said, let's go ahead and model the deuteron and include a correction due to, well, when the pion exchange happens, it notices whether you're on resonance or off resonance. If you're off resonance in one direction, the pion exchange gives a potential that's weaker and more limited. If you go in the other direction, it gets to be stronger and extends further. So this is the pion exchange in the case of a pseudo-scalar interaction. The pseudo-vector interaction for single pion exchange is going to work exactly the same way. So I can take, I took the Hamada-Johnson potential just because it was easy and I've worked with it before. I added the off-resonant corrections to the central and tensor potentials. And here's what happened. So when you're on resonance right here, then there's no correction and the binding energy is 2.22 MeV. But if you go off resonance in one direction where you have more energy available, then the binding energy gets to be bigger and bigger and bigger. And these are gigantic corrections off of resonance. If you go the other way, the binding energy gets to be weaker. So what we learned from this exercise is that the off-resonant energy shifts are large, which is incredibly good for this approach in this model. In the case of the dineutron, which I can also model easily, I find that the dineutron's normally not bound on resonance. But if you go off of resonance by about 25 MeV, then the attraction becomes strong enough to make the dineutron bound. If you have neutron clusters, they would expect to bind with less energy off of resonance. And that provides a possible interpretation for the Iwamura experiment. So if you start with palladium-110 and strontium-88, if you're producing excess heat, so you're putting the palladium off of resonance, then you have the chance of having the neutron cluster be bound. If it transfers to the strontium, then you can make strontium with heavier mass, and it can go down a decay chain and turn into molybdenum. And this, of course, is testable. Current status, we now have an overall theoretical picture that addresses many problems. We now have some experimental support that the excitation transfer actually happens. In fact, at this point, I think we have a picture that is capable of doing the job and turning into a quantitative theory that could be used for modeling and simulation. To make it work, I need these two matrix elements, the D2 going to helium-4 and HD going to helium-3. Last summer I worked on this one. I have a poster on it where I can show you the details. It's quite the calculation. It's not quite done yet. I expect it to be done like within a month or so, hopefully, and then we'll have a number. This one, I have an earlier estimate for this, but I got to redo it and do a better job. I want to do iron 57. I want to do this for the Lipinski experiment and get some phonon nuclear exchange for low-level metastable states. On my wish list, I'd like to see experiments get to the bottom of this weak nuclear emission, energetic particle emission effect. One example of it was by Chambers, where if you assume that D2 goes to helium-4, you get 24 MeV and give it to a palladium nucleus and dig out an alpha, the alpha comes out with on the order of 20, 21 MeV, which is what Chambers saw. So we're going to try to do experiment something like this and see whether we can correlate the alpha energy or the product energy to the host lattice. Another thing on the wish list is this, that if we have excitation transfer and many steps, and if it's non-resonant, if we pick up or lose some phonons each step, well, if you take 100,000 steps, then you're going to get an energy spread on the order of 10 eV. And that's actually observable in a bent crystal spectrometer experiment. I'm hoping to move towards simulation models. I think I'm far enough along that we could actually begin developing simulation models that could be used to test or to compare against excess heat experiments. And that's it. Thank you for your attention.
Okay. There is one serious flaw.
No problem, no problem.
Yeah.
Thanks.
I take over. There's one serious flaw with this reasoning because the frequency of terahertz is 10 to the 10 around, and the frequency of the deuterium is 10 to the 21. So we know from mechanics that coupling only can happen at wave peaks, must be in sync with the wave number. So we have a difference of 10 to 11. So you have to wait 1,000 years until the energy flows out. So this is simply not possible with this directly conversion of deuterium energy to phonon. We need intermediate steps with a stronger coupling. And one thing we see in experiments is that we have coupling with nuclear magnetic gamma states, as you see too. So then there must be one more step, because still the nuclear gamma step are at the level of 10 to power of 19 or 18, so we still would have to wait for 1 year. So from the transfer time, you can directly calculate the coupling energy. So in Pons-Fleischmann, we see that about 1 day at longest. With this, you get the coupling energy.
Okay.
Let's say there's some minor headaches with your argument. The coupling strength, of course, is not the phonon frequency. The coupling strength depends on the phonon nuclear coupling matrix element, which I described it. It depends on the strength of the vibrations. It depends on the number of nuclei involved. And in the experiments that Florian's been doing, one interpretation has it that we're actually transferring excitation in a time on the general order of a femtosecond per step to be consistent with experiment. Anyway, Kasagi, we can talk about it later.
Yeah, my simple question is, the effect seems like a Miss-Bauer effect. How can you recognize it's not a Miss-Bauer effect?
Okay, so Moss-Bauer effect is when you emit a gamma or you absorb a gamma, the gamma comes in with some momentum, the nucleus takes it and it rattles back and forth, and there's some probability you get no phonon exchange. This is, Lamb, or Moss-Bauer actually speculated about more general coupling, but he didn't work out a model for it. And in a sense, the model that's here is a sort of a direct generalization of these ideas. So it's got a relation to the Moss-Bauer effect, but this is definitely not a Moss-Bauer effect. How what?
No, excuse me, Hagelstein. Please, after. Here.
Yeah, Peter, I'm wondering how the coupling works between the excitation and the nuclei and the phonons. So in my view, the excitation is visible in the electromagnetic field, but not in a vibration in space direction. So a phonon is a vibration in space direction. How do they couple? I don't understand.
So normally I have some cartoons to show it, but one way to think about it is for the electronic case. Imagine you have an atom that has electrons in it that have a magnetic interaction. So if the electron is moving, then the movement, the velocity, will give rise to a magnetic field. And if another electron's moving the other way, then its motion will give a different magnetic field. Now if you take this atom and you start walking with it, then when you walk with it, the magnetic field gets stronger because you've added to the velocity, and that changes the magnetic field structure. So that it's called a boost correction, but the nuclear forces are momentum and velocity dependent. So if you take a nucleus, if you have it move uniformly, then if you go into the rest frame or the moving frame, nothing's changed. But on the other hand, if it moves one way and moves the other way, moves one way and moves the other way, then the internal nuclear force changes going this way, but then it turns around and changes the other way going backwards. So the motion is intimately coupled to the nuclear forces binding the nucleus in the first place. So this was discovered in 1937 by George Bright, and there's lots of papers and literature on it.
Okay. Do I understand?
Question, please. No, stop, please. I apologize, but the time is short.
I have just a quick question. That the lack of radiation is observed in...
No. Stop, please.
The lack of radiation is observed in many systems, such as nickel hydrogen, palladium deuteride, so the effect must be something general. And in your slides you presented about inertness of some sites, and so I was thinking that if there's general effect, it should not depend on the details of the crystal structure. So how do you reconcile these aspects?
Okay, so palladium is FCC, and vacancy formation in palladium is incredibly closely connected to vacancy formation in nickel. So the vacancies, they look a lot alike, they act a lot alike. The background electron density is very similar. And palladium, if you have a molecular hydrogen near palladium, it will bond as a molecule. Of all the other elements, nickel is pretty much closest to that, because a molecule actually, although it's not the ground state, it's very near the ground state, will bond as a molecule to the nickel. So although it's general, there are rules, and I think we need places with low background electron density to get the two deuterons to come together, or H and D to come together.
Another last question, very quickly. Yeah, go ahead.
Peter, I'd like to ask you about the duration of three main stages of your process. First one, duration of energy transferred between initial compound nucleus that created after fusion reaction to terahertz mode. Also, duration of propagation of such mode up to absorption with nearest nucleus, and also duration of excitation of formation of compound nuclei during the process of such interaction.
Okay.
3 pages. One stage, second one, and the third one.
Okay.
Your question's a really good question. Let me once again cite that from the excitation transfer experiments that Florian's been doing, the interpretation of the delocalization implies each transfer step takes on the order of a femtosecond. Now, this is in a system that's not optimized. The vibrations aren't all that strong. We could have a vibrational field 7 orders of magnitude stronger, and we could have many more nuclei involved as well, in principle. So, I mean, your question is the key question: how fast does this happen? The D2 to helium-4, because it's Coulomb limited, is the weak link. That's the slowest possible step. But that step is, as I have verified a number of times before, is sufficiently fast to support the experimental numbers for excess heat. The steps afterwards can be much faster. So the down conversion of 10 keV or 30 keV excited metastable state, that can easily be faster than a microsecond.
So typical duration about several femtoseconds, yes?
Again, it depends on what the transition is, the strength of the vibrations, how many are involved. And what I'm arguing is that we have an observation of a very fast femtosecond timescale transfer at this point from the data.
Thanks, Peter.